What do you remember about forces? Take a second and scan the QR code. Answer the questions, pause the video, and then come back after you have answered the questions. All right, let's review. All right, we talked about 5 main forces last year. We talked about the normal force. Let me turn my pencil on. Oops, sorry. All right, normal force. We talked about the frictional force. So remember, for these two forces, we need a solid surface. The normal force is the force provided by the surface. It's perpendicular to the surface. The friction is that interaction between two surfaces sliding against each other, and that one is drawn parallel to the surface. And it also opposes motion. We talked about the tension force. By the way, the labels for these is F for force, and then the subscript N for the normal force. F for friction, subscript, or F for force, little f for friction. Tension is F for force, T for tension. This you need a wire, a rope, a string, something you can pull tight. We also talked about a spring force. That is the force provided by a spring. This is also Hooke's law, and we will talk about that some more later. And then last but not least, we did the gravitational force, or force due to gravity. The spring force is F with an F, S for spring. Gravitation is F for force, G for gravitational. And remember, we had an equation for that, which was mass times the gravitational field strength. This year, we will also be talking about air resistance and drag forces. Our cycle for this is Newton's laws. Then we're going to do weightlessness and perceived gravity. And then we are going to talk about friction, and then we will talk about drag forces or resistive forces. All right, so forces present here. Well, we definitely always have gravity because it's in a gravitational field. There's no surface, so no normal or friction. No air resistance, it's not moving. Air resistance is a special type of friction, so it also requires motion. If there's no motion, you don't have any air resistance. No rope, string, or wire, so it's a spring here. So we have a spring force. Next one. All right, we have a ball shot into the air. They want while it's in the air. This is a projectile. Projectiles only have one force acting on them, and that is the force of gravity. You could also say there's air resistance, but just like we did last year, we tend to ignore it unless they tell us it is specifically there. All right, block sitting on a table at rest has gravity. We always have gravity even out in space. And we also have a normal force. No friction because there's no motion. No air resistance because there's no motion. No tension because there's no rope, string, or wire. And no spring because there's no spring. All right, a bucket being pulled out of a well. So we have a rope now. So we have a tension and we have a gravitational force. We drew force diagrams last year. The forces go in the direction that they act on the object. Gravitational force straight down. Tension force straight up. That would be our force diagram for the bucket. Depending on whether it's going, being accelerated upwards or if it's going at constant velocity, that's what would tell us how the tension force and the gravitational force relate to each other. All right, balanced or unbalanced. So balanced means I have a net force equal to 0. That's Newton's first law. Here we have a net force equal to mass times acceleration. So we would have something accelerating. So here we have our vertical forces that are equal. Oops, sorry. But my horizontal forces are also equal, so this one is balanced. It has a net force of equal to 0. This one has vertical forces that are equal, but this one is larger than the one over here, so this is an unbalanced. Acceleration is always in the direction of the unbalanced force. So for this one, acceleration would be to the right. This one has an unbalanced force going to the left, so its acceleration would be to the left. And then I asked, what direction is it moving? We can't determine the direction from the force diagram. So it can't be determined from an FBD. FBD is just my shorthand for a force body diagram or a free body diagram, force diagram, whatever. We don't know. We only know the direction of the acceleration. We could have this object moving to the right but slowing down because it's accelerating, or to the left, accelerating to the right means it would be slowing down. This one could be moving to the left and speeding up, or it could be moving to the right and slowing down. So velocity would be decreasing there, velocity would be increasing here. This would mean a decreasing velocity. If it was moving that way, it'd be an increasing velocity. We don't know if this one is at rest or if it has constant velocity. It could have constant velocity going to the left. It could have constant velocity going to the right. So we can't tell whether it's moving to the left or to the right or if it's at rest just from a free body diagram. All right, we can, however, tell from velocity time graphs. We can tell if it's balanced or unbalanced. This one's balanced, and it is on the positive side, so it is moving to the right. This one's on the positive side but slowing down, so that has a negative acceleration. That means it's unbalanced. You can also figure out the acceleration by looking at the slope of this line, which is negative. The slope of that line is positive. That means this one has a positive acceleration, so it must have unbalanced forces. So from these graphs, we can tell if it's at rest. None of these are at rest. If it was at rest, it would be on the x-axis like that. Balanced, moving with constant velocity for this first one, constant velocity. This one has an decreasing velocity. Goodness. Decreasing velocity. This one has an increasing velocity because the sign on the acceleration and the sign on my velocity is the same. They have opposite signs. It is slowing down. All right. Drawing force diagrams. So remember, normal force is perpendicular to the surface. Gravitational force goes straight down. A lot of problems now ask you to draw the force at the point of contact, so let me fix that one. The normal force would be right down to the surface. The gravitational force acts on the center of gravity. And then we have to have friction here because I'm going to say the block is at rest, and I did not say that specifically, but I'm going to say it now. So I have to have a frictional force here. So remember, when we draw these force diagrams, we have the gravitational force going down. We have the normal force perpendicular to the surface. I said there was friction on that one. Oh my goodness. I don't know why my pencil is advancing my slides. This is what my force diagram would look like. But then we have to do components. So I'm going to draw my y-axis right along my normal force. I'm going to draw my x-axis along my frictional force here. My y component of my gravitational force, I'm doing components for the gravitational force because that's the one that's not on the x or y axis. My y component comes down the normal. My x component goes along the x-axis parallel to it. That means my angle is going to be right there. I will do a separate video on calculating components and on drawing these force diagrams, and I will explain in that one why that angle is right there. But remember, thinking back, the frictional force is equal to this component if it's at rest or moving with constant velocity, and the normal force is equal to this component of the gravity if it's not accelerating up off from the platform or down through the platform. We will be doing a lot of problems that look like this this year with the tensions at angles, starting with the Monster Spider Lab on Friday, September 25th. So we have our forces here. We're going to draw our force diagram. We have our gravitational force going straight down. We have our tension force going at the angle there. We have our other tension force going horizontally that way. If we draw in an X and Y axis here, then this is the force that doesn't lie on our axes. So we have to draw in components here. We will have an horizontal component that goes along the x-axis, and we have a vertical component that goes along or parallel to the y-axis. And then, just a reminder, this vertical tension component of the tension force and the gravitational force are equal to each other. The horizontal tension force and the horizontal component of the tension force have to be equal to each other if this is a block that's at rest, which it most likely is, because having this accelerate would be a really crazy situation. All right, I hope that kind of helps with some of the quick review. The Newton's Laws summary should help you with some of the other stuff. Do the practice. Let me know if you have questions, and I'd be glad to help you. If you need a Zoom tutorial session, also let me know, and we can schedule one. Have a great day.